Welcome back to week 6, where we will be looking at feature engineering and model evaluation. Our day 1 will be introduction to feature engineering. Day 2 will be looking at data scaling and normalization. Day 3 will be going over encoding categorical variables. Day 4 will be looking at feature selection techniques, followed by on day 5 where we'll be looking at creating and transforming features. For day 6, we'll be looking at model evaluation techniques, and on day 7, we'll do cross validation and hyperparameter tuning. So let's get started with our week 6. Day 1, Introduction to Feature Engineering. So first, let's look at importance of feature engineering in machine learning. But before that, what is feature engineering? Now, feature engineering is the process of transforming raw data into meaningful inputs for machine learning models. It involves creating, modifying, or selecting features that enhance model performance. Now, why is feature engineering important? First, it improves model accuracy. Well engineered features provide more relevant information for the model, leading to better predictions. And that's what we have seen probably in the earlier videos. It reduces model complexity, simplifies the relationship that the model needs to learn, reducing the risk of overfitting. It enables model interpretability. Well constructed features can provide insights into the problem domain and help interpret model behavior. And it handles data challenges, addresses issues like missing data, irrelevant features, or scaling differences. Let's talk about some of the key applications in different sectors. In finance, aggregating transaction data for fraud detection. In healthcare, we have encoding categorical patient information for disease prediction. And in e commerce, transforming user activity logs into purchase predictions. Let's talk about different types of features. We have categorical, numerical, and ordinal. Now, with categorical features, it represents discrete categories or labels. Example can be gender, which is male or female, and color can be red, blue, or green. Encoding techniques that are used are one-hot encoding and label encoding. And in numerical features, it represents continuous or discrete numbers. Example is age, salary, temperature. Pre-processing techniques here is scaling. Example can be min-max scaling or standardization. And finally, we have the ordinal features, which represents categorical data with a meaningful order. Example can be education level, which is can be high school, bachelor, master's, PhD. So it's in particular order. And encoding techniques here is ordinal encoding. Now let's talk about overview of feature engineering techniques. So first is scaling. Ensures all features contribute equally to the model. The techniques that we use here are min-max scaling, which scales features to a range of 0 to 1. And then we have standardization, which centers the features around 0 with a standard deviation of 1. Next, we have encoding, which converts categorical data into numerical format. The techniques used, as we mentioned earlier, the one-hot encoding, which creates binary columns for each category. And we also have label encoding, which assigns numerical labels to the categories. Let's talk about transformation. Now, this applies mathematical functions to modify features. Examples can be log transformations, which reduces skewness in data, and polynomial features, which adds higher order terms for non-linear relationship. Next is feature selection. This reduces the number of input features to improve model performance. Techniques used here include statistical methods, example ANOVA or chi-square, which we have done in I think second or third week, and we have recursive feature elimination, which is RFE. Now, with all these in mind, let's go and look at a hands-on exercise. The thing that we'll be looking at is loading a dataset and explore its features, identifying some categorical and numerical features. And next, we'll plan which feature engineering techniques might be most suitable for the dataset. So here the objective again is to explore and analyze a dataset to identify different types of features and plan appropriate feature engineering techniques. We will be using the Titanic dataset that we have used before. The Titanic dataset contains information about passengers such as age, gender, ticket class, and survival status. So let's go ahead and follow our steps. First, let's create a new file, say Python file, save it as day1 underscore exercise. And here, first I want to load the dataset and explore the different features that are there. So I am going to say import pandas as PD. Next step is to load the Titanic dataset. Now that Titanic dataset is available in the GitHub user content. So I am going to just paste that here, https raw.githubusercontent.com data science do dojo datasets master titanic.csv. That's where you'll find it. Next, df equal to pd dot read CSV. So I'm going to read this CSV into a data frame. There you go, data frame. Next step is to display the dataset information. So I am going to say display dataset information. So I'm going to say print dataset info /n, and I'll say print df dot info, so we can look at the columns and what data it has. Next, let's go ahead and preview the first few rows. We'll be using the .head function here. So I'm going to say print /n dataset preview /n, and then go ahead and print df.head. So this will show me the first 5 rows of this dataset. So I'm going to open my terminal. I am going to say Python day1 underscore ex, increase the size. So here is my dataset information where it says I have passenger ID, survived, P class, name, sex, age, SIP, SP, barge, ticket, fare, cabin, embarked. And you see here, some of them are ints, some of them are objects, name and sex, probably male, female, and this is actual name, which is strings, float 64, int, again there's ticket, which is object, float, and then cabin and embarked are also objects. So we can see different, we kind of went through and explored the features that we have right now. Here is our data preview. Next is to identify categorical and numerical features. So that's what we did here, but let's go ahead and do it in code. So I am going to say separate features. I'll say categorical underscore features equal to df dot select d types include equal to object dot columns. So what it does is it looks at which ones are object, that's what we did, which are categorical features, and that's what is assigned to categorical features. Next, let's go ahead and do one for numerical features. So df, almost same, so I'm going to just copy this, dot select d types include, in this case I'm going to say include the int64, and this is numerical, oops, and I also want to use float 64. So these are my data sets that I have. So that's what I want to include inside my numerical features. Now let's go ahead and print. We already saw them, but it's good to see if these functions work. Features is categorical features, and sometimes you don't want to see like all the different fields and you want to automatically, in this case we have only 11 or 12 different columns, so you exactly can pinpoint, but sometimes you have like 300-400 columns and it's not possible to go and look at all of them, all the different features, and this is the best way to do it. Numerical features, and I'm going to say numerical features. Oh, of course I'll have to convert that to list, to display to list. So this will display in a list format. So I'm going to go ahead, clear it out, run it again, and there is an error here, /n. Let's try one more time, And there you go. It says categorical features are name, sex, ticket, cabin, and embarked. Name, sex, ticket, cabin, and embarked. And the rest of them probably went into the numerical features because they're all int64 or float64 types. Our next step is to plan feature engineering. So what I'm going to do here is, first step in here is, let's display summary of categorical features. I'm going to go ahead and comment out some of these print statements which we don't need. So first I'll say print /n categorical feature summary /n, and here I'm going to go through each and every column. So for call in categorical features, I'm going to say print f whatever this column is /n and comma df column dot value counts comma /n. So I've said f whatever this column is :n and then give the value count for that and go to the next line. Next I will say display summary of numerical features. Do the same thing here. Oops, I'll say print numerical feature summary, and then here I am going to directly go ahead and say print. I don't have to do too much, I don't have to loop through them. Numerical features dot describe. That's it, because these are different particular value counts and these are numbers, so we can use the describe to get the different statistics that are available. And if I go ahead and run it, clear it out, run it, I'll first see the categorical and numerical columns, and then right here category feature summary. So this is like all the names probably are only once, that's why I'm saying name is this times. Sex, we have male and female, which shows how many male and how many female are there. Tickets, what are the different types of tickets values that are there? These are 7, these 3 types are 7 times, these are repeated 6 times. Next we have cabin, different types of cabin, how many times they're repeated. Embarked, we have 3 different types, S, C, and Q. And then we see the numerical feature summary for the count, mean, standard deviation, min, max. So these values are displayed here. So we have all that data displayed for both categorical and numerical. Next, we need to document the feature engineering plan. So in this case, we'll probably first document the categorical features, where for gender, we will apply based on, because we have 2 different values. Let me just run this again. So for gender, we have 2 different values, male and female. So we'll apply one hot encoding for sex because it can have either binary values, yeah, male and female, so 0 and 1. Embarked will fill the missing values and encode the categories. That's what we'll do for embarked, because embarked has S, C, and Q. So we probably have to make sure that. And for ordinal features, which is P class, now the P class is available right here, where is inside. Let's move a little bit to the right here, and we have the P class here. Now for this we'll use ordinal features, because encode as ordinal values. 1 is less than 2 is less than 3, because the class is the class of the passenger, first class, second class, or third class. So we have 891 of them, but it displays the values based on the class here. So the deliverables for these are, there's 2 different deliverables. One is feature analyst report, where we list where this is a list of categorical, numerical, and ordinal features, and summary statistics for each feature type. And for feature, and the second deliverable is a feature engineering plan with clear documentation of pre-processing steps for each feature. So that kind of wraps up our exercise, and we got both our tasks done. And now, just to summarize, we understood the importance of feature engineering in machine learning pipelines. We went through and identified categorical, numerical, and ordinal features in a data set. We planned suitable feature engineering techniques for each feature type, and we prepared data set for machine learning models through effective feature preprocessing. So I hope you were able to follow along, and if you have any questions or doubts or had some issues implementing this, let me know in the message and I'll get back to you. Day 2, data scaling and normalization. Let's talk about the importance of scaling and normalization in machine learning. Now, what is scaling and normalization? Scaling and normalization are pre-processing techniques used to transform your numerical features to a common range or distribution, ensuring that no feature dominates the model due to its magnitude. What is scaling and normalization? Scaling and normalization are pre-processing techniques used to transform numerical features to a common range or distribution, ensuring that no feature dominates the model due to its magnitude. Now, why is scaling and normalization important? First, it improves algorithm performance. Many machine learning algorithms, such as k nearest neighbors (KNN), support vector machines (SVM), and gradient descent based models are sensitive to feature magnitudes. Now, features with larger scales can disproportionately influence distance metrics or optimization processes. Ensures fair comparisons. Standardizing feature scales allow the model to treat all features equally, leading to more balanced and fair learning, and stabilizes training. Algorithms like gradient descent converge faster with scaled features because the cost surface becomes more symmetric. Let's look at some of the methods with min-max scaling, standardization, also called as the z-score scaling. So with min-max scaling, transforms your features to a specified range type, typically 0 to 1, and ensures all the feature values are within the same range. Use cases for this can be algorithms like KNN or neural networks that rely on distance metrics or gradients. Limitations include it's sensitive to outliers, as extreme values can distort the scale. As per standardization or z-score scaling, centers the data around 0 and scales it to have a standard deviation of 1, and it ensures a standard normal distribution for each feature. Use cases for this is preferred for algorithms like SVM, logistic regression, and PCA. Advantages: handles outliers better than the min-max scaling. Now, when to use scaling and normalization for different algorithms? Now, algorithms that require scaling are distance based algorithms, which are KNN, SVM, K means clustering. These rely on distance metrics that are sensitive to feature magnitudes. Gradient based models, linear regression, logistic regression, and neural networks. Scaling accelerates convergence during training here. And algorithm less sensitive to scaling are tree-based models. Decision trees, we have random forest and gradient boosting. These models split data based on thresholds and are not affected by feature magnitudes. Let's go ahead and jump into hands-on exercise. First, we'll apply the min-max scaling and standardization to a dataset using the scikit-learn, and then observe the effects of scaling on model performance by training a KNN classifier before and after scaling. So the objective here is to apply min-max scaling and standardization to the iris dataset using scikit-learn. Compare the performance of a KNN classifier before and after scaling. So the data set again is the iris data set that we'll be using, which contains features like sepal length, sepal width, petal length, and petal width, which are used to classify flowers into 3 species. So now let's go ahead and start with a new project. I'm going to save it as day2 underscore exercise.py. Here, our first step is to load and explore the dataset. So I'm going to say from sklearn dot datasets import load underscore iris. Next, I am going to import pandas as PD. Next, let's go ahead and load the iris dataset. So for that, I'm going to say data equal to load iris, call that function. Next, I'm going to say x equal to our feature set pd dot data frame, and to this I'll pass data dot data, and columns that I'm interested are data dot feature underscore names. So that's it. And now y equal to our data dot target. Perfect. So we have our data set. Now let's display some data set information. So display data set information. First, let's go ahead and say print dataset info. Next line, I'm going to say print x dot describe. So this will describe all the stats for me. And then I'm going to say print /n target classes. And here I am going to say data dot target underscore names. Perfect. So I'm going to go ahead and let's see if we're in the same. Okay, perfect. And I'm going to say python day2.ex underscore ex.py, and here you go. We have our target classes, which are Setosa, versicolor, and virginica. These are the three different species the flowers are sorted into. And we have our information about the data set: count, mean, standard deviation, minimum, 25%, 50%, 75%, and max. It has its values over here. We have a count of 150 rows, so perfect. So we have enough data to play with. Now our step 2 is to train the KNN classifier without scaling. So for that I need from sklearn dot I'll use the model selection to import train test split. Next, from sklearn dot neighbors, I will import the function or class the k neighbors classifier, which I've used before. From sklearn dot metrics, we will import the accuracy score to check the accuracy of the model. Next, let's go ahead and split the data set. To split it, we'll do the same thing: x underscore train, x underscore test, y underscore train, and y underscore test. My testing and training data will be coming from train test split. I'll pass it x comma y comma test size equal to 0.2 and a random state equal to 42. Perfect. Next thing I will do is I'll train the KNN classifier. To do that, I'm going to say KNN equal to k neighbors classifier and pass it n underscore. How many neighbors do I need? 5 is what I'll use for this example. And then I'll say KNN dot fit. I'll fit it with x underscore training data and y underscore training data. Next, let's go ahead and predict and evaluate. So to predict, I'm going to say ypred equal to knn dot predict and pass it x underscore test. And for evaluating, I'm going to say print accuracy without scaling should be good because we are using the actual data like set provided by sklearn. Y underscore test comma y underscore pred. Perfect. Let's go ahead and run this. I'm going to clear it out, run it. I'll get the same information plus accuracy without scaling is 1.2, so it's pretty accurate. 100% accuracy is always good. Next one, what we're going to do is, now I'm going to give you an example. I mean, even though it's accurate, let's see what happens after we, or how we apply the min max scaling. Now to do that, I would probably need sklearn dot pre-processing, and I'm going to import from that min max scalar. That's what I'll use. And then what I'm going to do right now is I am going to do the same thing again. I'll say apply min max scaling, and I'll say scalar equal to, first create an instance of that, min max scalar. There you go. And then I'm going to say x underscore scaled equal to scalar dot fit underscore transform, and pass the value of x to this. Next, I will say, let's go ahead and split scale data, move it up a little bit, and here I'll say x underscore train underscore scaled, comma x underscore test underscore scaled, y underscore train underscore scaled, and y underscore test underscore scaled equal to train test split. Again, we'll use the not the actual data but whatever we scaled here, x underscore scaled, and then I'll give the y is same, test size is 0.2, and random state equal to 42. So make sure everything is right. Perfect. Our next step here is to now train KNN classifier on scale data. So before we did without scale data, this time I'm scaling KNN scaled equal to k neighbors classifier n neighbors equal to, give the same number 5, so we can see the difference, scaled dot fit. I'm going to pass x underscore train underscore scaled and y underscore train underscore scaled to this time. Let's go ahead and predict and evaluate. This time I'm going to say y underscore pred underscore scaled equal to knn underscore scaled dot predict, and pass x underscore test underscore scaled, and I'll say print accuracy with min max scaling is accuracy score, and pass it y underscore test underscore scaled and y underscore pred underscore scaled. So there you go. That's all that we need to do. Exactly same step but before and after scaling. So let's go ahead and clear this out and look at the differences. So if you see without scaling and with scaling is the same 1.2 because our data set is pretty optimized, so it should give you good data, good output. But if you try with something else, something that is available from one of those previous projects that we have done, you can try it out and then see the different formats. Our next step is to apply standardization. Now to apply standardization to the existing file, I need one more library, sklearn dot preprocessing, and from there I will import standard scalar, or you can always say comma standard scalar because I already have this here. Now I'll do the same thing as we did with this here. So instead of, I'm gonna copy most of it, since why do we need to type it again when we already have it. So apply standardization here. I'm going to say scalar equal to standard scalar this time, x underscore, I'm going to call stnd stand equal to scalar dot fit transform x, split the standardized data. Now here I'm going to say std std standardized and standardized and stand. So I have all this data here exactly same as before. The only difference is I've called it standardized train KNN classify on the standardized data. So I am going to say same thing here. I'm going to copy this stand classify fit and then x, this was std, this is std y, I'm going to use it std standardized knn predict. This is not the knn stand dot predict x test, not this std accuracy with standardization is accuracy score, pass the y stand and predict standardization. Now clear it out and run it. Now we'll have three different options, one with scaling, without scaling, min-max scaling, and then finally standardization. So try these with different data sets and let me know how it goes. But the final step here is to compare the results. Compare the accuracy of all the three of them classified before and after applying scaling techniques. Observe how the scaling improves performance by allowing the algorithm to use distance metrics effectively, but not here. But in your data set, if you use another data set, you'll probably see the differences. Now, just to summarize, we went through and looked at importance of scaling and normalization in machine learning. We learned when to use min-max scaling versus standardization for specific algorithms. We observed the effects of scaling on model performance through practical implementation, and this helped us gain proficiency in using scikit-learn for pre-processing and scaling datasets. I hope you were able to follow along and build this with me. If you have any questions or had any issues while implementing this, let me know and I'll get back to you. Day 3, Encoding Categorical Variables. Today we're going to look at one-hot encoding, label encoding, and their applications first. So what are the categorical variables? Categorical variables are features that represent discrete categories or labels. For example, we have binary categorical features, for example, gender, which can be male or female. And we have multi-class categorical features, for example, country can be USA, Canada, UK, and others. Since machine learning algorithms require numerical inputs, categorical variables must be transformed into numerical representations. So one option is one-hot encoding. One-hot encoding creates binary columns for each category in a categorical feature. Each row is marked with a 1 for its respective category and 0 elsewhere. Example can be feature color equal to red, blue, and green. So this is encoded something like this. We have red, blue, and green. It's 1 0 0 0 1 0. So we have three different rows, and depending on which row is marked by which row it represents is marked as 1, whereas the others are marked as zeros. The applications for this is effective for categorical features with a small number of unique categories and commonly used in tree-based models, logistic regression, and neural networks. Next, we have the label encoding. Label encoding assigns a unique integer to each category. Example, red equal to 0, blue equal to 1, and green equal to 2. You have three multiple values. And the application for this is suitable for ordinal features where the order matters. Example, high school is smaller than bachelor is smaller than masters, and can introduce unintentional ordinal relationship for nominal features. Some of the limitations that it has is it can mislead algorithms into interpreting categories as ordered, especially when the variable is nominal. Let's talk about dealing with high cardinality categorical features. Now, high cardinality categorical features contain a large number of unique categories. Example can be city names, product IDs. Now, the challenges here are first is dimensionality. One hot encoding creates too many columns, increasing computational costs. Next is sparse representation. Many columns have a value of 0, leading to sparsity in the dataset, as you see from the previous example of the colors. Solutions for this is frequency encoding. You can replace categories with their occurrence frequency in the dataset. Example is, let's say if city equal to NY, LA, NY, SF, and LA, then encoded value says NY equal to 2, LA is 2, and SF equal to 1. Next is target encoding. You can replace categories with the mean of the target variable for each category. Often used in supervised learning tasks, this target encoding is. Now let's look at when to use different encoding techniques. There's a table for it. When the encoding technique is one hot encoding, the use case is nominal feature with a small number of unique categories. For label encoding, it's ordinal features or when used with algorithms like tree-based models. Frequency encoding use case could be high cardinality features in both regression and classification tasks. And the target encoding is high cardinality features in supervised learning tasks. So with this in mind, let's go into our hands-on exercise. Exercise here is to apply one hot encoding and label encoding to a dataset with categorical variables. And then experiment with different encoding techniques and observe their impact on the model performance. So the objective again is to experiment with different encoding techniques on a dataset containing categorical variables and observe their impact on model performance. The dataset we will use here will be the Titanic dataset, which contains features like sex, when did the user embark, and the class P class for encoding. Let's go ahead and start with our steps. So first, I am going to create a new file, Python file, save it as day3 underscore exercise. First, let's go ahead and import. So first step is pretty much to load and explore the data set, which we've been doing. So I'm going to say pandas as PD. Then I'll go ahead and load the Titanic data set. Have the URL handy here, raw.github usercontent.com from data science dojo /datasets master titanic.csv. Next, I'm going to create a data frame equal to pd.read csv and pass the URL to it. There you go. Next, I'm going to go ahead and display dataset information as we've been doing. So for that, I'm going to say print dataset info, and then I'll say print df.info. Next, I'll go ahead and preview the first few rows here. To do that, I can say print /n dataset preview and print df.head, which will show us the first 5 rows of this data set. So that's the first step. So let's go ahead and run this. I'm going to say python day3.ex.py, and we have our Titanic dataset loaded here, and you can see not everything is int or numerical, so we have some objects here which will need to apply one hot encoding. So step 2 is to apply one hot encoding. So to apply the one hot encoding, I'm gonna go ahead and say apply one hot encoding. So to do that, I'll say df underscore one underscore hot equal to pd dot get dummies. That's the function that is available, and you say give the df, and you'll say columns equal to the ones that I'm interested to add one hot encoding is first sex, and the second one is embarked. And then I'll say drop first to true. So there you go. So we have our one hot encoding added. Next, I'm going to go ahead and say display the encoded data set, where I'm going to say print /n one hot encoded data set. So let's look at how it looks like. We'll go ahead and say print df underscore one hot dot head. So we'll see the difference between the two. Save it. We already ran earlier, so I'm going to run it again. So this is my normal data set, and this is my one hot encoding for sex equal to male is true or false, and embarked q and embarked s, embarked q. So it created different row columns for each one of them. Before it was s and c and q. Now it created different columns. If you look at the columns has increased as comparison to the previous ones, and it dropped some of them. So that's how this works. Now next step is to apply the label encoding. So I'm going to go here, and label encoding is applied to ordinal or nominal features like p class, assigning integers to each category. So what I'm going to do first is go here and say from sklearn dot preprocessing, I am going to import label encoder. And then to apply that, I am going to go down here and say apply label encoding. So I'm going to create a label encoder equal to label encoder. Next, I will go ahead and say df. In this time, I want to create a p class underscore encoded equal to label underscore encoder dot fit underscore transform. Into it, I'll pass the df p class. So that will apply the encoding to that label encoding. And now I'm going to say display encoded data set. So I am going to say print /n label encoded data set, print df. I'm going to just print p class and p class underscore encoded just to show the difference. And I'll say dot head, just show the top 5. That's good. I'm going to go back, clear it out, and run it again. And we have the actual ones, and then here is the encoded one, which where it assigned values based on I think 0, 1, and 2 to the different columns, to different classes. Now next thing we want to do is experiment with the high cardinality encoding. Now to do that, so for high cardinality features like ticket, frequency encoding can reduce dimensionality and sparsity. So what we are going to do here is, first I'll say apply frequency encoding, and here I'm going to say df of ticket underscore frequency equal to df of ticket, make sure this is not a typo, and map that to your df of ticket dot value underscore counts. So this will give me the value counts for those. Is a function, so I'll do that. And then finally I'll say display frequency encoded feature. So I'm going to say print /n frequency encoded feature. For that, I'll say print df of, so this time what all I'm interested in. So I'm interested in the ticket, the actual one, and then I am interested in the one that I created recently, which is this one, ticket frequency. I'm going to pass that inside here, and I just want to see the first 5 of them. Save it, clear it out, run it. Should be the last one that prints out. Here is our ticket numbers and how many times they have appeared. So this ticket appeared twice, this ticket appeared once. So that's how it does the high cardinality encoding. Now next thing is to compare the model performance before and after encoding. So we will train a classification model, example logistic regression, using both encoded data sets and compare the results. So I'm going to go back, and here I will say from sklearn dot model selection, I want to import train test split. From sklearn dot linear model, import logistic regression, and then from sklearn dot metrics, I want to import accuracy score. So once I have that, let's see, we have our data here, we have data frame here. So what we're going to do is we are going to first define features and target. So I'll go at the end here and say x equal to say df underscore one hot. From that I'm going to say drop columns. That columns that I'm not interested in are, let's say, survived. I'm not interested in name. I'm not interested in ticket, and one more is cabin. Okay, and then the target is df of survived. That's the one that I'm interested as a target, and rest of them can be dropped. So next I'm going to go ahead and split my data set, say x underscore train comma x underscore test comma y underscore train and y underscore test equal to train test split, and pass it x comma y test size, the usual stuff, 0.2, and random state equal to 42. Once I've done with that, I'm going to go ahead and train logistic regression model, and I'll say model equal to logistic regression model. How many iterations do I want? Max iterations equal to, let's keep it to 200, and model dot fit, I will say x underscore train comma y underscore train. Okay, so I have that. And finally, let's go ahead and predict and evaluate the model. So to predict, y underscore pred equal to model dot predict, and to that I'll pass x underscore test, and then print accuracy with one hot encoding is, say, accuracy score y test and y pred. So this will help us to kind of evaluate. So let's go ahead, clear it out, run again. Gonna give me everything up. I think I misspelled here, so of course it's gonna give me error. And there you go. So after running it, it says total number of iterations reached limit. Anyways, that we can ignore that. But here you go. Accuracy with one hot encoding is 0.77, which is pretty good, close to 1. So it's good. And there you go. We completed our hands-on exercise where we applied one hot encoding and label encoding to a data set with categorical variables and did an experiment with different encoding. So while working on this project, if you had any issues or have any other questions, do let me know and I'll get back to you. So just to summarize, today we went and understood and implemented different encoding techniques for categorical variables. We chose appropriate encoding methods for nominal, ordinal, and high cardinality features. We observed the impact of encoding techniques on machine learning model performance, and all this helped us gain some practical experience in using encoding techniques with real-world data sets. If you have any problems or questions based on whatever we did today, let me know and I'll get back to you. Day 4. Today we are going to look at some feature selection techniques. So first, let me give you an introduction to feature selection. What is feature selection? Feature selection is the process of identifying and retaining the most relevant features, which are also called as input variables, in a data set while discarding irrelevant or redundant ones. This step helps simplify the model, reduce overfitting, and improve computational efficiency. Now, why is feature selection important? It improves model performance. Irrelevant features can introduce noise and negatively impact predictions. It reduces overfitting. Simplifying the dataset helps the model generalize better to unseen data. It enhances interpretability. A smaller set of relevant features makes the model easier to understand. Increases computational efficiency. Reduces the time and resources needed for training and inference. Now, when to use feature selection? First, high dimensional data. When the dataset has many features compared to the number of samples, example genomic data. Second, correlated features. When some features are redundant or strongly correlated. And third is reducing complexity. So build lightweight models for production environments. Next, let's look at techniques for feature selection. Now, feature selection methods are categorized into three main groups. First is the filter methods. These methods evaluate the relevance of features by analyzing their statistical properties in relation to the target variable. Examples can be correlation, which measures the linear relationship between features and the target. Example for that is Pearson correlation coefficient. Next, mutual information. Now it measures the dependency between features and the target, capturing non-linear relationship. Now when to use it? When you have quick evaluation of features before training a model, that's when you'll use filter methods. Next is the wrapper methods. Iteratively selects features by training and evaluating a model, optimizing performance metric. Now examples for this is first one is forward selection, which starts with a no feature and adds them one by one. And then there's backward elimination, which starts with all the features and removes them one by one. Now when to use? Useful when feature interactions are important but computationally expensive. Next one is the embedded methods. This performs feature selection as part of the model training process. Examples here are lasso regression and tree-based models. In lasso regression, it penalizes the large coefficient, shrinking some of them to zero. Whereas in tree-based models, it uses the feature importance metrics to rank features. When to use embedded methods? It's effective when training tree-based models or regularized regression. Now, let's jump into our hands-on exercise where we will use correlation and mutual information to select important features from a dataset and then apply a tree-based model, example random forest, to identify the most important features. So the objective here is to use the filter and embedded methods that we just learned to select important features from a dataset and compare the results. The dataset that we will be using here will be the diabetes dataset from scikit-learn library. So I am going to go jump in, start a new file, Python file, and here first step is to load and explore the dataset. So I'm going to say from sklearn.datasets import load underscore diabetes. And next I'm going to say import pandas as PD. First step, load the data set. To do that, I'm going to say data equal to load underscore diabetes, call that function. Next, I'm going to say df equal to pd dot data frame, and I'm going to say data dot data as the data value. Columns that I'm interested is data dot feature names, and for target I'll say equal to data dot target. Next, let's display the dataset information. So I'm going to say display dataset information. So I'm going to say print. First step is to print df dot head. Next, I'll print df dot info. Let's go ahead. Let's go ahead and save it first. On day 4, I'll say day 4 underscore ex. Save it. Next, I'm going to go open terminal and say Python day 4 ex and run it. And I should have my data set displayed right here. Perfect. My next step here would be do feature selection using correlation. So for that, I am going to first import Seaborn as SNS. Next, I am going to import matplotlib.pyplot as plt, and then I'm going to comment these out. I don't need them. Now, first step is to calculate the correlation matrix. Now, to do that, it's very simple. I can just say correlation underscore matrix equal to df.corr. Next, I am going to plot the heat map of this matrix. So to do that, I'm going to say plot dot figure is fixed size equal to, I'm going to say 10 by 8, so it fits properly on my screen. Next, I'm going to say SNS dot heat map and pass it the correlation matrix. I'll say annotate equal to true, and I want the color C map equal to cool warm. Perfect. So I have my plot ready. Next, I'm going to go and say title that I want for this is correlation matrix, and then I'll say plot dot show for this. Next, finally, in this particular step, we'll go and select features with high correlation to the target. So let's display them and say correlated underscore features equal to correlation matrix target dot sort underscore values ascending equal to false. This will select our correlated values that I need. Let's go ahead and say features most correlated with target are print correlated features. Perfect. So that's how we can get the correlated features. So before we go into feature selection using mutual information, let's go ahead and run this. And there you go. We have our matrix and it has all the mapping here. Now depending on that, so we can see here features most correlated with target is the target and BMI S5. So that's what we get here. We get the values here, and this is the matrix that we have. Our next step will be to for feature selection using mutual information. Now for this, I am going to add one more library, sklearn dot feature selection import mutual info regression. That's what I'll use. Now here at the bottom, I'm going to first separate the features and target. So I'll say x equal to df of dot drop columns equal to the one that we have, which is as target, and then y equal to df of target. Perfect. Next, I will go ahead and calculate mutual information. This I can do by saying mutual underscore info equal to mutual. From my info regression, I can pass x comma y to this function. Next, I will create a data frame for better visualization. This data frame can be, I will say me.df equal to pd.data frame, and to this data frame I'll pass first feature as x dot columns, and then mutual information should be mutual underscore info, then me underscore df. Again, now I'll say me underscore df dot sorted by values, and in here I'll say by equal to mutual information comma ascending equal to false, something that we did last time too. And then let's go ahead and print the mutual information scores, print MEDF.
Perfect. Let's go ahead and run it. It will of course show all the previous things. So I'm going to close this. And here is my mutual information BMI, S5. This is the order in which it suggests me which is the best features to keep. Next is feature selection using the tree-based model. So I'm going to close this out. Let me go ahead and comment out the prints and the plots because we don't care about them right now. Okay, rest of them can stay. Now I'm going to go here and as I mentioned, it's feature selection using a tree-based model. So for that, I will go to sklearn, ensemble, and import my random forest regressor. That's what I need. And I'm going to say import numpy as np. First, let's go ahead and train a random forest model. This is model equal to random forest regressor, and I'm going to give a random state equal to 42, my favorite number. Model dot fit, I will give x comma y. These are the same things that we keep on doing before. Get feature importance here. Now for this I'm going to say feature underscore importance equal to model dot feature importances. This is already there. Importance underscore df equal to pd dot data frame. This is same as what we did earlier, but here I am going to say feature is x dot columns and importance is feature underscore importance. So that's what we'll pass. Next, I'm going to say again to sort it out, importance df equal to importance df dot sort by values by importance and ascending equal to false. Perfect. It's the same as before. And then I'm going to go ahead and say feature importance from random forest, just to differentiate between the others, but I've removed all the print cases anyways. So this is the only thing that we'll see, which is importance df. Next, if you want to plot this out, let's go ahead and do that too. Plot feature importance, plot dot figure. I'm gonna use a figure size of, let's say in this case 10,6. I think last one was a little big. Next, a plot dot barh. I want to pass the importance df feature and importance df importance. Perfect. And I'll say plot dot gca, and I will invert the y-axis, and then give a title to this where I'll say feature importance from random forest, and then say plot dot show. Keep it simple, run it, clear it out. Okay, this is already cleared. Run it, and we have our data here, S5 BMI. So depending on, so this is based on the tree based model selection, and this kind of shows you in a graph of which feature is more important for our model. So there you go. Perfect. So we kind of did bunch of different feature selection tools where we looked at first using correlation, then we saw using mutual information, and then finally we looked at how to do that using tree-based model. So depending on which one is perfect for your model, you can use that. Now just to summarize, today we understood why feature selection is critical for efficient machine learning workflows. We learned and applied various feature selection techniques including filter, wrapper, and embedded methods, and gained insights into using correlation, mutual information, and tree-based methods for selecting features. I hope you were able to follow along. If you have any questions or had any issues implementing the code, let me know and I'll get back to you. Day 5, creating and transforming features. Let's dive into feature creation first. Now, what is feature creation? Feature creation involves deriving new, meaningful features from existing ones to enhance a model's ability to capture important patterns in the data. These features are designed to provide additional information to improve the predictive power of the model. Example of feature creation involves first date time features. It extracts specific components such as day of the week, example Monday or Tuesday, can be a month of the year, January, February, or year or quarter. The use case is predicting sales trends where seasonality is important. Next, we have interaction features, where you combine two or more features to capture their interaction. Example can be multiplying area and price per square foot for real estate pricing. Then we have aggregations, where you create summary statistics like mean, sum, count for group data. Example can be customer purchase frequency on or average transaction amount. The importance of this is it adds domain knowledge to the dataset and captures hidden patterns and trends not evident in the original features. Let's talk about transforming the features. Now, what is feature transformation? Feature transformation modifies existing features to better suit the learning algorithm. This is especially important for handling skewed distributions or nonlinear relationships. Some of the common transformations are logarithmic transformations, which reduces skewness in highly skewed distributions. We have examples are applying log x to income data with extreme outliers. Now, next is square root transformation, which moderately reduces skewness, often used for count data. Example is applying root of x to event occurrence data. Then we have polynomial transformation, which adds higher order terms x square, x cube to capture nonlinear relationships. Example can be including x square when the relationship between features and target is quadratic. Importance of this is it enhances the model's ability to fit nonlinear relationships and makes distributions more normal, like aiding algorithms that assume normality. Now let's talk about the importance of feature transformation in nonlinear relationships. Transformations allow linear models to handle nonlinear relationships. For example, polynomial transformations enables linear regression to model quadratic patterns, whereas logarithmic transformations stabilize variance and handle the skewness. By transforming features, models become more robust and capable of capturing complex patterns in the data. With this in mind, let's jump into hands-on exercise. Our hands-on exercise includes creating a new feature from from the date column, example day of the week, month, year, and apply polynomial transformation to a data set and compare model performance before and after transformation. So objective again is to derive new features from a date column in a data set and then apply polynomial transformations and evaluate their impact on model performance. We will be using the bike sharing dataset, which contains information about bike rentals, including date, temperature, and rental count. Our step one is to load and explore the dataset. So first, let's go ahead. So I'm going to create a new file. I'll call it Python file. Save it in my day5 underscore ex. I already have the bike sharing daily.csv file here. So I can go open that. Let's go and say open dot. This is the file that I have, which has instant, date, day, season, year, month, all this information over here. So I'm going to use that file. So I'm going to copy the file name. Next, I'm going to say import pandas as PD. Now, first step is to load the bike sharing data set. So I am going to say file name equal to, or I can just say df equal to pd dot read csv, and to this csv I'll pass that csv file name. Next, let's go ahead and display dataset information. Now for that, I'm going to say print data set info, and I'll print df.info for this just to display. Next, as usual, preview the first few rows. So I'm going to say print /n dataset preview, and for this I'll say print df.head. Perfect. So I'm going to go and run that file, and we have my data preview here, which has the date field that we are talking about, and we have a bunch of different columns that are available. Perfect. Our next step is to create new features from the date column. So we'll extract the components from the date column, such as the date of the week and month, to capture seasonality and trends. So I'm going to go here and I will say convert DTE day to date time. The way to do it is I'll say df of DTE day equal to pd dot to underscore date time, and pass it that field of df of, let's make sure we are picking the right one, DTE day. Perfect. Next, let's go ahead and create new features. First one that I want to create is day of the week. Day of week, that's what I'll call it. Let's say df DTE day dot dt dot day name. That's how you get the name of the day. Next, I'm going to say df month equal to df dt day dot dt dot month. Next, for the year, I'm going to say df year equal to df dt day dot dt dot year. So probably you guessed it already. Next, let's go ahead and display the new features. Say print /n new features derived from date column equal to print df, and here I will display first one DTE day, which is our existing one. Next one is day of the week, so I'm going to copy paste this here. Next, I need month, easier to type. Here I have everything, dot head. I think I got this out. Perfect. There you go. Perfect. So now let's run this and check out our, clear it out. I'm going to run it. And there you go. We have DTE day, day of the week, month, and year, all of them removed from this particular field here. Perfect. Our next step is to apply the polynomial transformation. Now, polynomial transformations help capture the non-linear relationship in numerical features such as the temperatures that we have. So what we're going to do first is from sklearn dot preprocessing, I'm going to import that amazing function called as polynomial features, which we used once before. So first I am going to say select feature and target. I'm going to say x equal to df of the feature that I want. In this particular case is temperature. Let's see if it's there, right? Just so that we're not making up stuff. So temperature is there, which is of the type float64. So next I am going to say y equal to df of CNT. That is my that is the count of number of rentals that is there. Next I am going to say apply polynomial transformation. I'll say poly equal to polynomial features degree equal to Day 6, Model Evaluation Techniques. Let's look at some of the evaluation metrics for regression. So, to go over the regression metrics, first we have the mean absolute error, or MAE. This measures the average magnitude of errors without considering their direction. Use case for mean absolute error is it suitable when all errors have equal importance. Next, let's talk about mean square error, or MSE. This measures the average of square differences between actual and predicted values. The use case for this is it penalizes larger errors more than MAE, making it sensitive to outliers. Next, root mean square error, or RMSE. It's a square root of MSE providing errors in the same units as the target variable. The use case, it's a common metric for interpretability in real world units. Next, let's talk about R squared. This measures how well the model explains the variability of the target variable. Use case indicates the proportion of variance explained by the model. Next, let's look at evaluation metrics for classification. Classification metrics include accuracy, which is percentage of correctly classified instances. As we mentioned earlier, accuracy is calculated as true positives plus true negatives divided by true positives plus true negatives plus false positives and false negatives. Use case for this is suitable for balanced data sets but misleading for imbalanced data. Next, we have precision, is the fraction of true positive predictions among all positive predictions. The usual formula for this is true positives divided by true positives plus false positives, and its use case is important when false positives are costly. Example, spam detection. Then we have recall, or also called as sensitivity, which is the fraction of true positives identified among all actual positives. So it's true positives divided by true positives plus false negatives. And the use case for this is critical in situations where missing positives is costly. Example can be medical diagnosis. Next, we have F1 score. It's the harmonic mean of precision and recall, and for it, the use case is useful for imbalanced data sets. Then we have ROC AUC, which measures the ability of the model to distinguish between classes. Its use case is it important for evaluating binary classifiers. Next, let's understand when to use any of these metrics. So in regression, we use MAE for interpretability and uniform importance of errors. We use MSE or RMSE when the larger errors need greater penalization. And we use R square to explain variance but not as a sole performance metric. Then in classification, we use accuracy for balanced data sets. We use precision and recall for imbalanced data sets depending on the problem's focus. Example can be minimizing false positives or false negatives. We use F1 score for a balanced evaluation of precision and recall. And we use ROC AUC for overall model performance evaluation in binary classification. Let's jump into hands-on exercise. Today, we'll be doing two exercises. Exercise 1 will be classification model evaluation, where the objective is to train a classification model, calculate the confusion matrix, and interpret precision, recall, and F1 score. The dataset we'll be using here is the IRIS dataset, focusing on binary classification tasks, example, classifying one species versus others. So let's get started. Let's start with a new file, save it as day6 underscore exercise.py. And here first, let's get our data set from sklearn.dataset import load iris. We need the train test split, so that is coming from sklearn.model selection import train test split, and then from sklearn.linear model we will import logistic regression, and then we need the different metrics from sklearn dot metrics, we will import confusion matrix, classification report, and we will also get the confusion matrix display. So that's to start with. Now let's go ahead and load our data set, which is our iris data set, that I can say by load by saying load underscore iris function. Next, I'll do my features. I'll say data dot data, that will get me all the features, and then I'll say y equal to data dot target if equal to 0 as type int. So for binary classification, we're saying class 0 versus others. Next, I am going to split the data set by calling train test split and pass it the features, target, test size equal to 0.2 and random state equal to 42, and this will give me x underscore train, x underscore test, y underscore train, and y underscore test. Perfect. Next, let's go ahead and train the logistic regression model. Now to do that, I'm going to say model equal to logistic regression. That's how I initialize it. Next, I'm going to say model dot fit and fit x train and y train. Next, let's go ahead and predict. To predict, I'm going to say y underscore predict equal to model dot predict and pass it x underscore test for prediction. Let's move this a little bit to the top. So now the prediction is done. Let's go ahead and display the confusion matrix, or get the confusion matrix, that I can say cm equal to confusion matrix, and it pass y test and the prediction y underscore pred. So that will give me the confusion matrix. Now for display, I'm going to create a variable display and say confusion matrix display, and to this it needs the confusion matrix, which in our case is cm. Okay, let's get rid of this, and I'm going to say display label. So it needs the display labels which we are saying class 0 and not class 0. So for that, I am going to give a list saying not class 0 and class 0. So these are my display labels. So now once that is done, next thing that I need to do is I'm going to plot this display by using CMap. My colors is I want to use blues. Next, I want to give a title to the plot, and I'll call it confusion matrix, and then I'm going to say plot dot show. So this will create my plot and then show my plot. Now looks like I am missing something here, so I'm going to say from matplotlib dot pyplot as a, I'll say import as plt, so that warnings will go away. So now next, once this is done, let's go ahead and use the classification metrics that we have also gotten. So I'm going to say classification metrics is print /n classification report. Now to create that, I'll say print classification report, and to it needs the test data y underscore test, and it needs the predicted data y underscore pred. Perfect. So I have that. I think I have used y underscore predict, and that's why it's giving me error everywhere. Perfect. So there you go. That's perfect. Now go back here, and I'm gonna say Python day 6 underscore, and there you go. We have our confusion matrix here, class 0, class not class 0, and they have the matrix displayed depending on where most of them lies. So not class 0 has more than class 0. And next, let's look at the classification report. We have pretty perfect score because we're using a pre-built data set which will work perfectly for our linear regression model. Our next exercise is the regression model evaluation. Now in this, the objective is to train a regression model and evaluate its performance using the MAE, MSE, and R square. So let's go ahead and implement that. We'll be using the California housing dataset to predict the house prices in this particular case. So I am going to go here, clear this out, create a new and save it as exercise 2.py. And in here, first I need my libraries. So first California data, sklearn.datasets. I'm going to import fetch California housing. Next, from sklearn.model selection, I am going to import train test split. Next, from sklearn.linear model, I am going to import linear regression. Next, I need the metrics from sklearn.metrics. I am going to import mean, MAE, mean absolute error, MSE, mean squared error, and then R square, which is R2 score. Perfect. So these are the different functions that are available for us, and we don't have to actually use the formula for it. Perfect. So I'm going to say load data set, and for that I'm going to get my data from fetch California housing. Next I'm going to say X and Y, my features and target are data.data and data.target. Kind of best to use the Scikit data set, you get everything aligned for you. Then next I'll go ahead and split the data set. Then I use X train, X test, Y train, and Y test for these, and say train test split, pass it X, Y, test size equal to 0.2, and random state equal to 42, the usual stuff. Next, let's go ahead and train my linear regression model. So I'm going to say model equal to linear regression. Next, let's go and fit and train the data by saying X underscore train and Y underscore train. So this will train my model. Now once I am training the model, the next step is always to predict. So I'm going to go ahead and say predict, where I will create ypred equal to model dot predict and pass it X underscore test to predict the data sets, and based on that I can go ahead and evaluate the regression metrics, my MAE, which is mean absolute error, and to this I can pass the text data and the ypred data not equal to. Next, for MSE is the same thing, mean squared error, and it needs the same information. For R2, again same thing, R2 score, and it needs the same parameters. So given that I've calculated all these, now let's go ahead and print these. First one is mean absolute error, which is MAE, and to display that in line I'm going to say MAE colon 0.2f. I don't want to see the extra decimals. For next one is mean squared error, which is MSE. For that I'm going to use MSE. And finally, for R2 score or R square, I am going to say R2. Yep, perfect. So sounds good. So they are all been printed. Let's go ahead and run this. I'm going to say Python day 6 exercise 2 .py, and there you go. We have mean absolute error as 0.53, squared error is 0.56, and R2 score is 0.58, like this. Okay, but you get the point. It's much easier to use these existing function and get the data based on the modeled linear regression model that we have. So we were able to train a regression model and evaluate its performance using MAE, MSE, and R square. So I hope you were able to follow along. If not, let me know and I'll get back to you. So just to summarize, today we went through and learned some key evaluation metrics for regression and classification tasks. Then we went and understood when to use a specific metric based on problem type and data characteristics. Next, we went over and did some hands-on experience calculating exercises, calculating the and interpreting evaluation metrics, and we developed insights into model performance and areas for improvement. So if you have any questions or any issues you faced while building these applications, let me know and I'll get back to you. Day 7, cross validation and hyperparameter tuning. So let's first dive into introduction to cross validation. So what is cross validation? Cross validation is a technique used to assess how well a machine learning model generalizes to an independent dataset. It splits the data into multiple subsets called as folds, ensuring that each data point is used for both training and validation. Now let's talk about different types of cross validation. We have the k-fold cross validation, which splits the dataset into k folds of approximately equal size. Then the model is trained on k-1 folds and validated on the remaining fold. This process is repeated k times and the average performance is computed. Next, we have the stratified k-fold, which ensures that each fold maintains the same class distribution as the original dataset and is useful for imbalanced datasets. Next, we have the leave one out cross validation, which is also called as LOOCV, which uses a single data point for validation and the rest for training. It repeats this process for all the data points and computationally expensive but provides the most robust evaluation. Next, let's look at hyperparameter tuning. Now, what is hyperparameter tuning? Hyperparameters are parameters that are not learned by the model but are set before training. Example, learning rate, number of trees, depth of a tree. Now, tuning these parameters or hyperparameters is crucial for optimizing model performance. Now, what are the techniques for hyperparameter tuning? We have grid search, which exhaustively searches over a predefined hyperparameter space. Example here is testing all combination of values for max depth and learning rate. Then we have the random search, which randomly samples combinations of hyperparameters from the predefined space. It's more efficient than grid search when the parameter space is large. Next, what is the importance of hyperparameter tuning? It prevents overfitting and underfitting by selecting the best configuration, enhances model performance by optimizing critical settings. Next, let's talk about importance of tuning hyperparameters for model performance. Now, without tuning, the model might not reach its optimal performance, leading to first underfitting, where model fails to capture the underlying patterns, or maybe overfitting, where model memorizes the training data and performs poorly on unseen data. So let's jump into our end of the week hands-on project, which is based on feature engineering and model evaluation. The objective here is to perform end-to-end feature engineering, model evaluation, and hyperparameter tuning on a dataset. The dataset that we have picked here is the Titanic dataset, which contains passenger information to predict survival, and that survival field is survived. Now, the task that we'll follow here is first, we'll perform feature engineering. Next, we'll train and evaluate the model. Next, we are going to apply the grid search for hyperparameter tuning, and that's about it. So let's get started. First, I'm going to create a new file, save it in my day 7 project. And here, let's start with our task 1, which is perform feature engineering. Now, we'll be doing 3 things: feature scaling, which standardize numerical features to ensure they contribute equally. Next, we are going to do feature encoding, where encode categorical features using techniques like one-hot encoding. And finally, we'll do feature selection, where select the most relevant features based on correlation or feature importance. Go ahead and import pandas as PD. We will get from sklearn dot preprocessing import the standard scalar and one hot encoder. Next, we'll get compose sklearn dot compose, and from here we will import the column transformer. Perfect. Now that we have this, our data set is coming from a particular GitHub user, Nick dataset, which is this one, GitHub usercontent.com, data science dojo, datasets master, titanics.csv. Now to read this, I am converted into a data frame. I'm going to say pd.read csv, pass the URL to it. Next, let's go ahead and first let me quickly print df.head to make sure that this exists. I'm going to say Python day 7, and there you go, we have the data set. Perfect. And clear this out, remove this, and next we'll select the relevant fields from there. So I'll say select relevant features. Now if I open this, let me open this URL. Here is our URL that we are calling. Now the thing that I'm interested here is T class, sex, age, we have fair, that is interesting, embarked, and also we need survived. So I'm going to copy this entire thing, and here I am going to say first what we need is df equal to df of. Now the only field that I'm interested is what I'm going to put in here, T class. Next I want sex. Next I want age. Next I want fair. I want embarked, and then I want survived. So these are the 6 different columns that I want. And next I am going to handle the missing values inside here. If you do an info, you'll probably see how many of them have missing values. So age has a bunch of missing values that I've seen. So I'm going to say fill NA, and I'm going to say df of age. Now this is an older way of doing it. There's a new method of filling these values. Median, I think it's going to give me a warning, but I can change and show you how the new method looks like. True. Next I'm going to say df embarked dot fill NA, df of, so these two have some empty fields, and that's why I am filling them up. For this I am going to use the mode of 0th element, comma, in place equal to true. Now if I run this just the way it is, I think it's going to give me a warning, and there you go, it says that this is not the right way of doing it. The right way of doing it is use this particular method here. So I am going to do that, where it says, I'm going to put this in comment here. So this says df dot call the method which is fill NA, and then say which column that I'm interested in. I'm interested in age. So I'm going to say age is and the value is df of, this is the value that I want to set there, and in place equal to true. So I don't need this. Similarly, I can copy this one more time here, embarked, and this time I'm using mode of 0. Perfect. So that's what I'm going to do. Now let's run this again. Just do it side by side to see. See, nothing happened now. So this is the new way of doing it. The older one has been deprecated. Next, I am going to define features and target. So x equal to df of, or df dot drop. I don't need from my entire set. I don't need survived for my data, for my features. So I'm going to say remove survived from here. In my y, and my y equal to df of survived only. So that's my target. So now that is done. Next step is to apply the feature scaling and encoding. So I'm going to do that, feature scaling and encoding. For that, I'm going to say pre-processor equal to column transformer, and to this I am going to create transformers equal to the transformers that I'm interested in is first one for numbers num. I can say standard scalar, and that is for the fields of age and fair. So that's what I'm going to do here. Next, for categorical, I am going to use one hot encoder, and those are p class, sex, which is male and female, and embarked. Okay, so these are the three ones that are categorical. So that's good. And finally, I'm going to say x underscore pre-processed equal to, I'm going to pass it through that preprocessor dot fit transform and pass the values of x. And this is what will give me the pre-processed features available here. So that kind of completes our task one. Our task two is to train and evaluate models. So we'll be training like we can multiple models. We can use logistic regression, random forest, and we can evaluate these models using cross validation to ensure like robust performance between them. So first, I am going to import from sklearn dot model selection. I am going to import cross value score. So that's first. Next, from linear model, sklearn dot linear model, I am going to import the logistic regression, and we said that we're going to use random forest, and that is available in sklearn dot ensemble import random forest classifier. Perfect. Now that we have these, let's go ahead and train and evaluate logistic regression first. So I'll say logistic regression model equal to logistic regression, initialize that. Next, I'm going to say logistic scores equal to, I use the cross-val score. Did I import the wrong one? Yep. Cross-val, not predict, but score. Use the cross-val score, and here I am going to pass the model. I'll pass the x underscore pre-processed. I'm going to pass the y, which are the targets. I'll say CV equal to 5 cross validation, and the scoring equal to, I'm going to use accuracy for this because, as I mentioned, there's different metrics available. Accuracy is best for this one, and I am going to print my logistic regression accuracy, which is, and log underscore scores dot, let's take the mean of that, and I don't need to see all the decimals. I'm going to say 0.2f. That's perfect. So that should take care of it. Similarly, next, let's go ahead and train and evaluate random forest. It's the same functions. I would say random RF model equal to random forest classifier, and it needs a random state. So random state equal to 42 RF scores equal to cross val score. Use the same function. This time I'm going to pass RF model. I'm going to pass the pre-processed data. I'm going to pass y. I'll use the same CV as 5 cross validation point, and scoring. In this case, I'm going to use the same one, accuracy. Spelling is right. Yes, perfect. So that's good. Next, once that is done, I can print my random forest accuracy to RF scores dot mean point to f. Perfect. So let's go ahead and test both of them. I'm going to go ahead and run the project. And there you go. We have the logistic regression accuracy of 0.79 and random forest accuracy of 0.81. So you see the difference between the two of them based on the data set that we have pre-processed. Our task 3 now is to apply grid search for hyperparameter tuning. We'll use the grid search to optimize hyperparameters for the random forest model and then evaluate the best model in this particular case. So I'm going to go ahead here and first move all the way to the top, and I need the grid search. So that is available in sklearn dot model selection. Inside that, I can import grid search CV. There you go. That's what we need. Now let's define the hyperparameter grid. So first I go and define hyperparameter grid, and the different thing that the parameter grid will have different parameters that I'm focusing on. Is first one is n underscore estimators, which I will take as 50, 100 and 200. Next, I'm going to use max underscore depth, which is, I'll say none, to 10 to 20. Next, I am going to use the minimum samples split. For this hyperparameter, I'll set 2, 5 and 10, some of the standard values that I always use. Now let's go ahead and perform the grid search. Now to do the grid search, I'm going to create a parameter, say grid variable grid search, and call the function grid search CV. Now it needs the different parameters that it needs. First is it needs an estimator. So in this case, I'm going to use random forest classifier. We give the same value, random state 42, so it's the same data set. Next, I will say next it needs is the parameter grid, which is what we have created above. So I'm going to give that parameter grid as a value. Next, it needs what type of scoring I'm using. I will be using accuracy. Next, I will need the CV, which is 5. We're going to give the same value, and number of jobs that it wants to run, and jobs equal to -1. Perfect. So that should take care of it. Next step is to now grid underscore search dot fit my x underscore pre-processed and my y values. So now once I have that, let's go ahead, play the best hyper parameters and score. So for this, I am going to say print f of best hyperparameters is grid underscore search dot, it has this best parameters available here. I'm going to just display that. Next, I am going to say print f of best accuracy, say grid search dot best, and this one is best score, and I want point to f, don't want to see the entire thing. Save it. Let's go back, clear it out, run it again. So we'll also see the previous project stuff, which is logistic regression accuracy, random forest accuracy, and the best hyperparameters here is out of the ones that we have created. Max depth is 10, minimum sample split has 5, and n estimator is 50. So based on the parameters that we provided, it picked me the best parameters that I can use, and the best accuracy it got based on these hyperparameters is 0.83, which is better than what we got from random forest accuracy before. So based on whatever we did here, using feature engineering, we pre-processed features, scaled and encoded and for modeling. Next, we did the cross-validation, where we used reliable performance estimates for logistic regression and random forest. And then finally, hyperparameter tuning. We took different values here and improved the model accuracy by selecting optimal hyperparameters for the random forest model. That's kind of concludes our project and our week. So just to summarize, today we went over and understood the importance of cross validation in evaluating machine learning models. We applied feature engineering techniques including scaling, encoding and selection. We performed our hyperparameter tuning using the grid search to optimize model performance, and finally, based on this, we gained some hands-on experience in building an end-to-end machine learning workflow. I hope you were able to follow along, and if you have any questions or had any issues while implementing this, let me know and I'll get back to you.